All right, section 8.3, electron shells, subshells, and orbitals. Think about this as we're trying to figure out an idea. We're using quantum mechanics to figure out where approximately each electron is within an atom. Okay, so we're going to explain the spatial arrangement in which electrons are distributed around the nucleus. Okay, so the ideas that led to this were work done by de Broglie, who proposed that matter has both wave-like and particle-like properties, and developed an equation to calculate the wavelength of a moving electron from its mass and velocity. Also, the Heisenberg uncertainty principle. He said that the velocity of an electron is due to its wave-like nature and its position is due to its particle-like nature. Because of this, you cannot know both the velocity and position of an electron simultaneously. The more accurately you know one, the less accurately you can know the other. So the quantum mechanical model of an atom utilized that, but was also taking into consideration the Schrödinger wave equation. When solved, gives a 3D distribution map for the probable position of an electron in an atom. An electron orbital is a region of space surrounding the nucleus where an electron is likely to be found. Okay, so that's a very important term, orbital. An orbital is a region of space around a nucleus where an electron is likely to be found. Orbitals have different shapes and sizes. Now, that's another very important thing, and we're going to almost jump right into these different orbital shapes. So any orbital can hold a maximum of 2 electrons. Next up, a subshell is a group of orbitals with the same energy. There are 4 different types of subshells designated S, P, D, and F. An S subshell contains 1 orbital, a P subshell 3, a D subshell 5, and an F subshell 7. Now, an electron shell or principal energy level N is a grouping of subshells. N equals 1, 2, 3. It's going to be a positive value. Now, the first energy level, or the first shell, is made up of 1 subshell, while the second contains 2 subshells. The third contains 3 subshells. The lower energy shells, or electron shells, are closer to the nucleus, and they contain fewer subshells and can hold fewer electrons. Higher energy electron shells extend farther from the nucleus, contain more subshells, and can hold more electrons. But one thing that I need you to keep in mind here is each orbital can only hold 2 electrons. All right, so if you remember what I was talking about a little while ago, I said that an orbital was something that could hold 2 electrons. So that means this guy right here holds 2 electrons. This guy right here is a p sub x orbital. This is the p sub y. This is the p sub z orbital. These are 3 distinct orbitals. This holds 2 electrons, 2 electrons, and 2 electrons. So if we compare these two, the s orbital, how many electrons does that hold? Okay, now the p orbital, how many does that hold? Well, the p orbital, or the p orbitals, px, py, and pz, all collectively hold 6 electrons. So I always like to say this as the s orbital holds 2 electrons. The p orbital, since the p orbital has 3 different positions, it's going to hold a total of 6 electrons. To further develop that, the d orbital, well, that has a total of 5 different positions. 2, 2, 2, 2, and 2. So the d orbitals will hold a total of 10 electrons. Now this right here shows sort of a relative sizes of orbitals. And I think that it's a good way to look at, well, what does an atom consist of? And let's go ahead and do this. So if you imagine at the exact center of this right here, where I'm very lightly drawing a single dot, that's your nucleus. This one s orbital holds 2 electrons. The 2s orbital is kind of the next place that you can put electrons as close to the nucleus as possible. And so this will hold 2 electrons. And what I want you to be visualizing here is we're building an atom. Okay, so I put 2 electrons as close to my nucleus as possible, and those go into my 1s orbital. Then I want to put 2 more electrons. And the next place that they're going to go is into my 2s orbital. So now I've got 4 electrons placed. The first 2 in the 1s, the next 2 in the 2s orbital. Now, after that, I'm going to put them in my 2px, 2py, 2pz. So 2, 2, and 2 electrons. So this will hold a grand total of 6 electrons. These px, py, pz, that's as close as I can put the electrons, while also being kind of repelled by the 1s electrons and the 2s electrons. So at this point in time, where I'm going to draw a line right here, I've placed a total of 10 electrons around my nucleus. The next place I can put them are my 3s orbital. After the 3s orbital, we'll go to 3px, py, pz. So this would be 2, and this would be 6. So I'm talking about placing a grand total of 18 electrons. Now, with that as kind of a model, can you say anything about, well, how many electrons does, or sorry, can you say anything about the identity of this atom? Yeah, you can. What is something that in its ground state has 18 electrons? Well, the element argon. This is known as basically the electron configuration for an element, and specifically this is the electron configuration for the element of argon. All right, so as you can see, this gets more and more complicated, but effectively what we're trying to do is we're trying to place electrons here. We're trying to place electrons around a nucleus so that we can say, well, where are all of the electrons roughly of a particular element or of a particular atom? I hope this is helpful. This is definitely sort of abstract, but with practice, looking at electron configuration, you're going to get better and better at this. All right, I hope this is helpful. You got this.